Swayam Prabha. Digital India. Educated India.
Good morning everyone, welcome you all to this course on the analytical spectral microscopy applications of inorganic compounds, inorganic systems and nanomaterials. In the previous class I have talked to you about what is the focus of this course and who will get benefited, etc. Let us start with a topic on atomic absorption, because I will be speaking very not so deeply in this, because it is a very simple technique, direct technique. Directly you can correlate between the concentration and the signal part of it. One thing let me tell you, that it is not necessary, I will be showing a lot of instrumentation things, but there is no need for you to learn to know the physics of the instrumentation, the electronics of the instrumentation, but you need to know the configuration of the instrumentation, what are all the items functioning in that, and because of that what kind of a signal you are getting. So those are quite alright thing. Now atomic absorption spectroscopy, also atomic emission spectroscopy, both of these we will look at together under the atomic absorption spectroscopy. So atomic absorption or emission. So this is one of the analytical techniques that people use very quite often, but as the title says, that whatever the compound you take, whatever the molecule you take, whatever the salt you take, you convert into atoms on that. So obviously it is a destructive method, you cannot reconstruct back that one. So other thing is just straightforward, whatever the signal strength comes, which is proportional to your concentration. So let us look at what exactly this. In case of absorption, the light absorbed and certain electronic transitions taking place in that atom, not in that molecule. After converting into the atom, your molecule is converted into the atom, your compound is converted into the corresponding atom. So that in that atom. In the emission spectroscopy, it is the excited electronic state returning back to the ground state, releases an energy or h nu, and that is what you are using for the emission part of it. Okay. So in the atomic absorption spectroscopy, as you can see, that you need to convert into the atoms. To convert into the atom, obviously you have to break the bonds of that. So what you do is you essentially take your compound or molecule and put into one of the examples that I have shown here is the flame. So the flame is used here. So as I mentioned that I am talking to you about the atomic absorption, and similarly I will take emission, but I will not speak twice, but we take as general as the atomic absorption spectroscopy. First you need to make this into atoms, obviously. Yes, so you put your compound into this flame and the flame converts this into the atoms, and those atoms will absorb the light, and then that is what you are basically measuring. And in this case the light is coming from this particular unit called hollow cathode lamp. I will explain you just in a while, hold on that, no problem. And there is only one specific wavelength of the light comes out, and this light is captured by only one type of atoms that are present in that. So you take your sample in this, and then the sample is being nebulized into this, aspirated, nebulized, and then put into this particular flame, get the atomization. So what are the kinds of processes happening? You have a sample, then you get into the nebulization, then you get into the flame that will first remove the solvent, desolvation, then once the solvent is removed, then volatilization, then it will break into the atoms, and that is what the kind of different processes that one can visualize what is happening in the flame. So I hope that gives a clarity to you what is, and then comes at the end is your atoms, and these atoms are being used for your absorption spectroscopy. Okay. So I hope now the sampling part, the atomization part is clear to you. There are so many processes are happening before that, and then comes is the atomization then. Now once you have the atoms, then you want to measure the signal by the light method, and you need to get some light. And these are atoms, they have a sharp transitions from one electronic level to the other, and therefore you don't require a very broad the light signal. So you have a very sharp light signal. The sharp light signals can only be generated again from the excited atoms, and that's what is done in the hollow cathode lamp. Okay, so now in this case, one of the constraint in this is, suppose if you have a nickel or copper or a silver, for each one of that you need to use one different hollow cathode lamp. Now if you have a mixture, then you have to change the hollow cathode lamps during the analysis. That's a big constraint restriction. But in the initial days, this itself is a very good technique people have used a lot for analysis. When you want to expedite the analysis, now you have many other techniques have come up in that. So if you look at on the right bottom of this is the hollow cathode lamp. The hollow cathode lamp is the cathode portion, and the anode portions are here. Anode portions are outer jacket, inner is a hollow cathode, and this is where you coat the material. Suppose we want to have the nickel coating, gold coating, silver coating, copper coating, platinum coating, whatever is there as a cathode. And this what happens is you have an inert gas, and then this inert gas is kind of ionized, and that will hit on this and then dissolve, excite the atoms in this what you have, and then give the light, and that light is being used. So this whole thing you can think in terms of this is the hollow cathode lamp, which is expanded version of that. So as I said to you once again, let me clarify, each one of the cathode lamp can give only one H nu value. So if your the solution has got more than one atom to be measured, then you need to change the hollow cathode lamp. So that is the kind of a thing that constraint that you have. So just again explain to you here is the principle. You have basically atomization. Each atom will absorb very selectively a particular wavelength, and also your cathode lamp will give very selectively that particular energy. So therefore there is a resonance between the light coming out from your cathode and the light being absorbed by your atom. But when you have a mixture, then you have to change the cathodes frequently, therefore it becomes a very inconvenient kind of thing. There are many other limitations were there, though it was used in the early 60s etc. as a technique, but now it is not so much used because you have other techniques are being utilized available, and they will help you to reduce any kind of a limitations. In the flame technique, what is there? For example, flame, in the next slide or so I will be showing different regions of the flame, they are not the same. So if your compound gets into one region, the ionization, atomization will be different from if it is in another region, if it is in another region of the flame itself. So therefore you have a variety of kinds of things. So this is basically the noise created by the flame zones itself, and the other thing is each cathode lamp can give only one, so therefore only one atom, one type of atom, not one atom, one type of atom you can excite at one time. So that is another constraint. And when you put your sample into the flame, 95% of the sample or even 98% of the sample is being wasted. You use only very little of that. And as I said, that temperature profiles of the flame are different, which I will be explaining you in a while, which is dependent on the height of the flame, the ratio of the oxidant versus the fuel ratio, and the rate at which you pass these things, all of these kind of things. So therefore different extents of atomization, different extents of the ionization. So in this flame, when you use, so you have a lot of atomizations, ionizations, and complexations also occur. So there, all of these are there happening into that different regions, which I will explain you in a while. So therefore you have all these pieces, whatever the compounds you have. If your light passes through this, the atom will absorb. If it passes through this, it will absorb. If it passes through that, it will absorb that as well. So, therefore, your line spectrum will become very broad and then gives a lot of errors. So, that is what is called the limitations. So, there are several limitations on that too. So, as I mentioned to you, and these limitations are referred in terms of interferences. So, a lot of people are familiar with the word interferences, they are not so familiar with the limitations. So, the interferences come from the chemical nature itself, because the chemical nature of the atom, ion, complex are different. The same atom is present in that, but they are different. The ionization, to what extent the ionization is occurring, and what kind of a solvent that you have involved, what kind of a the reaction conditions like protonation, deprotonation things, and a variety of unwanted products are formed from the compounds. So, in different regions of the flame, I will be showing you just in a while, there are some regions where the oxygen is rich, some regions where the oxygen is low, etc. So, therefore, you have different kinds of things possible. In some cases, very low oxygen ratio, where the carbon content will be more, where there is a possibility the element can combine with the carbon and give the carbides. In the other region where the oxygen is rich, it can form the it can react with the oxygen and give the oxides kind of things. So, these are all kinds of different kinds of compounds. So, that is where you can see the complexation or the compounds. So, you have variety of these things are formed. So, their absorption lines will get broadened, and then absorption extents will be changing, therefore, your concentrations will vary. Besides this, a spectral interference, if you have not used a properly resolved light wavelength, obviously you have a width in the light of the wavelength, that will also be giving a aberration or interference or limitation kind of things. Just to give you a quick view at that, this is coming from the burner at the 1, 2, 3, you are using different levels of the gas flow, different. So, and with your the air which has got oxygen and your fuel, these have to be mixed, right? And here air is not there, so you get very low temperature kind of thing, very not so bright, not so high temperature thing. Then you add a little bit of air hole, you see the colors of the flames changing here, and you put some more and some more. So, you can see the bluish flame, and then the edges and the interior will change. So, if you take one such and analyze in 2 dimensions, one of the dimension is the height from the burner level to different regions. So, you can see that. So, the dark reddish, less reddish, orangish, yellowish, and then greenish and bluish. So, this tint, the color that is shown, will talk to you about the level of temperature. So, the blue is low, cool, that is called 300 is cool almost, and slightly bluish is reduced, in temperature is increased. Go to the green, going to 500 to 600 to 800 to 1000, etc. Go to somewhat little yellow, is a little higher temperature, orange maybe 1500, go to red, and this is much greater, much higher temperatures. So, the temperature profile is being built in this flame. Suppose your compound is here, sometimes your compound is here, your compound is here, your compound is here, whatever you are spraying, that is what you are doing. So, when you spray, your compound can go to this region, this region, this region. So, that is what you are looking at, different regions of that. So, you will have a different kinds of not only atoms will be there, but many other unwanted ionized products, unwanted compounds, unwanted complexes, all of those, they are all giving you wrong things. So, interference will be there. Okay. So, therefore, in order to control this, people have started understanding a little better and then used a different technique. The technique which is shown for atomization here is another one, which is called graphite furnace. So, graphite furnace is, your sample is somewhere in a boat inside this, and this whole thing is controlled under the atmosphere. Though it looks like as if it is open, it is not. There will be a window here, there will be a window here. That window allows the light come in, light going out, and then you make this into by heating. This graphite tube is heated by electrical wiring, and then when you heat, and certain exterior things should not be heat temperature, therefore you have a jacket which is put through which you pass the water, that will cool down, and this heating will heat only the sample, not the compartment, other part of the compartment, and therefore that will atomize without flame. There is no flame here, only thermal heating. Thermal heating is coming from the electrical. So, electrical flow will give the heat, and that heat will decompose this particular thing and give atomic. So, if somebody could not understand this, you can look into this. It is one and the same from different source I have taken, other direction. The light is coming from here and light is going out of this, and this is your chamber where you have the graphite furnace. So, this is the chamber where you have the graphite furnace, and in that you have a sample. So, you can see the sample platform. So, this is the graphite tube basically, and the remaining things. So, you maintain the inert gas flow, all other things. So, now there is no flame here. So, there is no way that you can get some ions, some compounds, etc., because there is no oxygen present, there is no carbon present into that. So, therefore, nothing to make into that kind of a compounds at all. So, you get pure atoms, and that atoms are absorbing your light, and then you can measure. So, this is one other modified measurement. There are other kinds of atomizations, glow discharge. That means you apply high potential torque wherein the inert gas like argon will form into their ions. You are not studying the argon. Argon is used to bombard on your compound and generate atoms. So, you have your compound, you put into the cathode, and this argon ions are generated from the anode and passing towards the cathode, and then when they pass towards the cathode, they will hit onto that particular target which has got your compound being coated, and there from there they will dislodge and then make the thing. So, this is what is called the sputtering process, and once the atoms come, of course, the remaining technique will be the same. Sometimes you can do a chemical kind of a method. So, the chemical method is you convert your atom or ion into a different compound. Why you make? Because that such a compound can be easily dissociated into the atoms. So, one such compounds are hydrides. So, you convert your arsenic or tin, selenium, bismuth, these kind of things, you treat with some things like acid, then add your sodium borohydride or other kind of hydrate sources, and this will give you the hydrate materials. And these hydrate materials can again be passed through either through this graphite kind of a furnace or some other atomization kind of a furnace, that kind of thing. For example, here you can see this reaction vessel where your hydrase is generated, and then it goes into that, and then you are using a quartz and then heating it up. You can also heat with either burner, you can also heat with a electrical also, not necessarily only this one, and then you can take your atoms out. So, your initially what you are forming is a hydrate compound of your ion or atom, and then that is being further broken down into the atom and hydrogen separately, and that atom is what you are measuring. At the end you are measuring only the atoms, not ions, not the compounds. Okay, so we talked about a few methods of atomization. One is the flame, other is the glow discharge, other is the discharge using the graphite furnace, and then converting into chemical and then breaking down. So, these are various methods. Then let us look at a little on the detection side of this. So, detection of course is absolutely an important aspect in this particular atomic absorption spectroscopy, whether you go for absorption or emission, any of these things. What are you detecting? You are not detecting that atom. That atom has absorbed a light, and that the light that it is absorbed basically, that is what you are basically measuring. In case of emission, that excited state is release the light, and that is what you are measuring. You are not measuring the atom, you are not measuring the ion, but they are that energy, that is that light energy which is absorbed is a very characteristic of that particular atom or the ion. That is where you are basically measuring the things. So, in this the detection, so what you need to detect the lambda which is absorbed and very selective kind of thing. This is used and your light signal is proportional to the concentration of your atoms that you have. So, therefore, other things should not be there. then your concentration errors will come, and that you have taken care by the method that you are using for atomization, and now you are measuring. So, this is now use the light coming in and falling onto these kind of a mirrors called dinodes, and then it will sort of increase. You see the line is thinner, became thicker, become big thicker, much more thicker, etc. So, that is what is that called? So, it is adding up, adding up, adding up. So, you are enhancing your signal by going through these dinodes by so basically they are the reflectors, and that will convert into the electrical signal which is measurable level. So, you can measure things like nano amperes kind of thing. So, you should bring down to the or bring up to the level of the nano amperes. If it is much lower amperes, it will not be measuring. So, that is why you are using multiple centers of these things, and these are called diodes, and the first light signal is hitting here and then increasing, it's further increasing further. So, therefore, you are making multiple levels of your thing, and that will increase the electrical signal that is being measured. At the end, what you are measuring is electrical. So, it is a basically electrical amplification of your light, and that is what. So, that we do not need to know the physics and the engineering part of that, and so this whole thing. So, now people are using charge coupled devices, and this is coming in terms of the pixels. So, if there are 200 pixels, means that 200 independent detectors, like here you have how many? So, 1, 2, 3, 4, 5, 6, 7, 8, 9, like that. So, like that you can have a large number. As you increase the number, multiplication will increase. So, therefore, your signal will be better. So, your sensitivity will be better, and that means even if you have a low concentration your atoms in that technique, you can even measure. Otherwise, you will not be able to measure the low concentration ones, then there is no use. So, that is where this detection method. So, one other thing which is being used in the recent days is the inductively coupled plasma atomic emission. Atomic absorption also are there, but not so popular. Atomic emission is being most commonly used. So, nowadays, and in fact, inductively coupled plasma is also attached to mass spectrometers and many other things. So, here it is atomic emission spectroscopy. This is a very powerful, you can measure the compounds at the level of pico or sub pico levels of concentrations too. In the conventional method, suppose if you use just the flame technique with the halocathode, you cannot measure those things, because the concentration, because there is no, those detectors which are used are not doing that much of a photomultiplication. Here they do huge amount of multiplication technique is used. So, this is uses the inductively coupled plasma. Plasma is used to provide excited atoms. That excited atoms are not your compound, that is a organ, other kind of a gas, and those bombard on your compound and generate your compound atoms. So, that is where, so you are using a plasma. When you use the plasma, your temperatures goes to 5,000, 10,000, 25,000 even. So, that means you need to cool down that. So, at a cool conditions, that is all used in these ones. And so, if you see here, you have your sample just like what you saw in the atomic absorption, there is no difference in that. Then you are going because you need to push that at a particular speed. So, you are pushing it through a pump, and the pump pushes through the nebulizer, and then you need to break it up into smaller particle sizes. So, that is what is called the aerosol things, and those fine particles are taken in and the remaining is thrown out. Okay. So, this is you refer in terms of the flow chamber or spray chamber into that, and from here you have almost like atom by atom going or particle by particle moving upwards, because very fine kind of a chamber you have. And when it comes towards the end, that is where you wanted to knock out and make the atoms out of that. For that you used this one, the RF coil. This RF coil thing with the power, that is what is the one which generates your plasma, and the plasma hits your particles and then create the flow of this looks like a flame, but there is no flame here. This is not a flame. Okay. So, it is the plasma hitting your compound and then making into atoms. So, this whole thing will have atoms, and this will be absorbed by the light, and the light you are measuring. So, the expanded version of this region is shown here. Okay. Coming from here, and your light comes here, falls on the grating, and then goes to the prism. So, now you have seen. And now what will do this grating and prism? They will resolve different types of lambdas. So, one type of lambda with another lambda, even with 0.1 nanometer difference, you can separate it out. So, you have different ones. So, you see the color line. This is one lambda, this is a different lambda, this is another lambda, this is another lambda. So, the lambdas are separated out, and then you can measure. So, what do you use? Use that coupling, inductively coupled plasma, which is used for the atomization part, and then for the detector use these CID detectors of each of these. So, you can get very fine information, even very low concentration signal that comes is a smaller, but it is being multiplied. You have seen in the previous slide, you have seen that this is multiplied, and what you are using is the charge coupled device, which will make into, depending upon the number of pixels. So, greater the number of the pixels, greater the signal, lesser the compound strength. Even if you are very small, you can still find out that. Okay. So, with this kind of a technique, you completely eliminate the difficulties that you find from the flame and the low resolution and many interferences. All those things are eliminated by doing this one. So, these have started becoming very popular, and simultaneously you do not need to change the cathode like that. So, whatever the radiation, suppose you have 4 or 5 different atoms are there present in your sample, each one gives one different characteristic lambda. So, therefore, you can measure simultaneously. So, you do not need to go one at a time. So, this is another thing. So, your measurement time becomes very rapid, very quick. So, you can easily measure. For example, this can be used for ecological samples, biological samples. So, ecological samples, a lot of pollutants, organic type, inorganic type, everything, and the biological, a lot of different kinds of things, geological kind of things, medical and food, atmospheric, agriculture, space. So, in a variety of areas you can bring the sample, put into this. So, therefore, you can analyze. So, you can analyze all of these simultaneously. So, you got the best method that is possible with atomic analysis. Of course, the sample is destroyed, you cannot recover the sample in all of this. So, this is some very simple, very basic kind of things that one need to know. All those people who wants to analyze their samples, whether the academic or industrial or research labs, to know that much only I have covered in this. So, to keep ourselves active, we need always some kind of a practice to be done. So, what I have thrown a practice for you is the practice by collecting the data of the lowest concentration detection ranges for all this. So, I have given you so many different kind of techniques, different kinds of the atomizers, different kinds of the detectors, etc. For them there is some limitation. So, please look into that. These are all data available, and put them together and put into a graph sheet and try to find out by yourself which method is better. This data is available. Okay. So, using the knowledge that I have given through this lecture, please put down your thinking. I have already addressed what kind of differences that you will have, what kind of interferences that you will have, what kind of problems you will face if you use a flame technique, which gives a lot of errors in the data as compared to the other techniques. The last technique which I have given you is ICP-AES, which has a much different. So, look at that, look at this technique and try to connect yourself how these modifications have changed the whole scenario of having the interferences, having the errors, having the data problems, etc. Of this. Okay. So, if somebody has a problem in understanding the principle that I made, I think nowadays everyone asks for animations. So, I have collected some information on this. So, you can, but be careful, the animation is only the animation, cannot give the true version of that. But if you are used to do that, yes, you can go ahead and look at that aspect of it and then no problem, but animations are not the true versions of it. Okay. So, with this I complete the atomic absorption, atomic emission part of it, and in the next class we can take up some separation techniques, and then we will go to thermal techniques on all these things. Thank you very much.